Hi everyone, in this video we're going to be looking at the standardized statistic and we're going to go take a little bit deeper dive into this. So remember what we said in the previous video. The standardized statistic is a way for us to measure how far our statistic that we actually got is from the middle of our chance model. And so remember, we're saying how far from the middle. And what I was trying to, the point I was trying to get across was the further from the middle you are, in general, the more extreme you're going to be, okay? But there's a little caveat here. We got to talk about this a little bit. And just as a reminder, remember the middle is the value from the null, right? So our example was Buzz and Doris. Buzz and Doris. We had 50%, right? They were just coin flipping it. Who knows? I'm just going to push a random button. I'm a dolphin. Well, we want to know how far away is 15 out of 16 from that? Is it far enough away to say, we don't think it's supposed to happen? Okay, so I mean, that doesn't sound hard, right? We showed you in the last one, you could just subtract two numbers and that tells you how far away they are. But there is an extra piece to this, okay? And so the extra piece is something I want to demonstrate to you using these two chance models that I've built. So these two chance models are still Buzz and Doris. So just to kind of give you the idea, this is still Buzz and Doris. Okay. This is still assuming 50%. So it's still 50-50. We think they're flipping coins. And that's why the mean, make sure you're paying attention to this piece. The mean, the middle of the picture is still 0.5. Okay, so let's think about this. Which of these two pictures is giving me more evidence? So what do I mean by that? Well, I claim that if you look at Buzz and Doris, the 15 out of 16, I claim that that's actually more extreme on one of these pictures than the other. So take a second, look at these pictures, and think about what I mean by that. How could these same two pictures, right, with the same middle, came from the same idea of simulating, coin flip, how could 15 out of 16 be more extreme on one of these than the other? You know, Mr. B said, I'm just trying to measure myself from the middle, and the middle is always the same. 15 out of 16 is the same. How could it be different? Well, these pictures, the way I've put them, are not scaled the way they really should be. So first of all, the vertical is not scaled the same, and that's not that important. The important thing is the horizontal axis is not scaled. So watch what I can do here. I'm going to take this first chance model. It has a mean of 0.5, and this SD here is the standard deviation that we had talked about in a previous video. Measures the spread. Okay, well, again, I got a middle of basically 0.5. Of course, that was my null hypothesis. But my standard deviation is 0.04, so it's smaller. What does that mean? A smaller standard deviation means the points should be more closely clumped together. But I don't really know. It seems like they're the same in this picture. Well, that's because I was being a little tricky with this picture. Pay attention to these values here. 0.38 to 0.64. Let's fit that into our picture here. 0.38 to 0.64. Have to go even smaller. Look at this. All of these dots fit into this little box in terms of their spread. So let's think about this. All of these dots fit in between 0.38 and 0.64. Every single simulation in this simulation I had gotten, every single one had a statistic between 3.8 and 6.4. That range is really not that big. Compare that to the range here. The range of values here, all the way from 0.2 maybe to, looks like maybe 0.88 actually got hit here. That's a much more spread out set of data. So what we're seeing here is that the data in this picture is much more clumped together. The data in this picture is much more spread out. So what the point is here is that even though in both of these scenarios, your statistic, 15 out of 16, is the same distance from the center, 0.5, 0.5. The idea here is this picture is more spread out, so your statistic is still closer to some of the samples, some of those statistics. It's still closer to some of the dots. Here, the 15 out of 16 is not really close to any dots. It's further not only from the middle, but from everything. And so that makes it more extreme. So what am I trying to say here? Let's actually draw this out. Let's take our statistic, 15 out of 16, and let's measure how far it is from the center of each of these. So let's start with the big one. So 15 out of 16 is right about here. So this is our 15 out of 16. Okay. So then if I measure the distance between those two, I'm going like this, right about here. So this purple line here, make it a little thicker so it's easier to see, right? That's, to me, measuring the distance between the center and the statistic. Okay, well, I just said that it's supposed to be the same. So well, let's look here. Let's go center, measure out to the statistic. Look, these are the same distance. So what am I talking about? Look, I got the same distance from the center to my statistic. Shouldn't that mean that they're the same amount of extremeness, right? No. Why? Look at this. Let's look a little closer. Look at the purple. This statistic hits some of the other samples already right here. So let's look right here. I'm already pretty close to some of the other samples in here. So while I am pretty extreme, right, I'm not going to say it's not extreme. It's pretty extreme in this purple case. I'm not that far from some of the other samples. So while I am unusual, you know, I'm not too far from at least some other samples that happened. But let's think about that in terms of the red line. In terms of the red line, the first time I hit a sample for this smaller chance model, look how far I have to go. All the way here. I've got to go what looks like over double the distance to get to my first sample that's in this smaller chance model. So not only am I quite a far distance away from the middle, but I'm actually really far from anything. So that means I'm more unusual or extreme, which means I've got even more evidence against the null. So it's not just how far you are from the middle, it's also got to be somehow measured how far you are from everything else. So it's not just the middle, it's how far you are from everything. And well, what's the key component there? Well, if everything is compact, small standard deviation, then me being far away will seem even more extreme. On the other hand, like this bigger distribution we have here, the bigger chance model, if we're more spread out, then even if I'm the same distance away from the middle, you know, I'm still close to some of the other samples, so it doesn't seem as extreme. So let me say it again. If my chance model is compact, small standard deviation, look at the standard deviation is really tiny, then being far away seems even more extreme than if my distribution, my big one, had a slightly bigger standard deviation, because that means my data is more spread out and I look more normal. So the same number, the same statistic can look more or less extreme based on your chance model being more or less spread out. So it can't just be how far you are, it's also got to be something about your actual chance model and how spread out the statistics in that the simulated statistics in that model are. And so with that in your mind, I know it's such a weird idea, right? You feel like I'm either far away or I'm not. Well, just that you're far away, it's that how extreme do you look? And if your chance model is very tightly compact, small standard deviation, you're going to look more extreme even if you're the same distance away. So how does that come up in the formula? Because this is one of our first formulas that we're going to be using here. How does that come up in the formula? It's actually not too bad. Here it is. The standardized statistic is equal to the statistic, because that's what we're looking at, right? You subtract the mean of the null distribution. Remember, that's just the center. That's just the raw distance between the two. But we just said that's not good enough, right? So how do we take into account how spread out our chance model is? We divide by the standard deviation of that chance model. We got to divide by the standard deviation. We are taking into account the standard deviation, the spread of it. So let's think about this. And this is, maybe you haven't done this in a while, but we can think about this. If I put a small number on the bottom of a fraction, it makes it big, the whole thing big. So the smaller the standard deviation, the more compact you are, your chance model is, the bigger your standardized statistic is. And a bigger standardized statistic means more extreme. Okay? So a bigger standardized statistic, more extreme. It's the opposite of p-value. So you just got to remember, p-value and standardized statistic, the extreme, the evidence, all of those ideas, it's the opposite way, right? Big standardized statistic, more evidence for the alternative. Small p-value, more evidence. This is going to be something that we get messed up sometimes, and that's okay. We just got to work at it. All right. So the only thing left to mention here, and it's not going to be a key point for us at all, is there are two standardized statistics that we'll deal with. And the way we're going to split the difference on these is we are going to just call the standardized statistic a z-score whenever you're dealing with categorical data proportions. If, on the other hand, you have means, averages, quantitative data, you're going to be using a t-score. And we're not going to get into why. There's, if you're interested, I'm happy to talk about it